In this chapter, we'll discuss chemical equilibrium. So we'll start out by just discussing the general concept of equilibrium. We'll then move into things like the equilibrium constant and how to use it. And lastly, we'll finish with Le Chatelier's principle. So let's start out by just discussing the general concept of equilibrium. So what exactly is equilibrium? So when we talk about chemical equilibrium, we're talking about reactions that are reversible. This means that we have a forward reaction and we also have a reverse reaction. And you'll know a system is at equilibrium when you see these equilibrium arrows. This tells you that this reaction can proceed in the forward direction or in the reverse direction. Okay? And this system can reach an equilibrium. What equilibrium means is that we have, at the same time, these reactants forming these products, and we simultaneously have these reactants forming these products. When we get to an equilibrium, if we have a dynamic equilibrium, just like we have with vapor pressure, the state of the reaction, or this is the state of the reaction when the rate of the forward reaction equals the rate of the reverse reaction. So rate F is equal to rate R. The forward reaction rate is equal to the reverse reaction rate. And at a state of dynamic equilibrium, the concentration of the products and reactants will be constant, but they're not necessarily the same. Okay, so once we reach true dynamic equilibrium, we have the forward reaction and the reverse reaction occurring at the same rate, so that the concentrations of our reactants and products aren't changing, but that doesn't necessarily mean that they're equal in quantity. A good analogy for this would be if you think of a mall. And we have up escalators and we have down escalators in a mall. So while people are upstairs wandering around the stores, and they eventually get bored and they want to go downstairs, maybe look at those stores. Okay, so they take the escalator down. Well, at the same time, we have shoppers in the bottom part of the stores, or in the bottom part of the mall, looking at those stores, and maybe they get tired of those stores, and now they want to go upstairs. Okay, so simultaneously we have people moving downstairs and upstairs at the same time. So this is just like an equilibrium reaction. So in an equilibrium reaction we have the forward reaction and the reverse reaction occurring simultaneously. So here's a look at an equilibrium system that we can actually observe with our eyes. Okay, so we have N2O4, which can decompose to give us NO2 gas. And it just so turns out that N2O4 is colorless and NO2 is brown. Okay, so what happens with this system is that we can actually observe the forward and the reverse reaction by either heating or cooling the system. So if left at a moderate temperature, we have something in the middle. So we end up with this sort of tan gas inside of a vial. But we can actually force the reverse reaction by cooling the system. And we can see that we can actually change the system from being a mixture of the two to being only the colorless gas by cooling it. Okay, so if we cool this reaction mixture, we end up with the colorless gas only. And we can see that by it actually changing color. If we take the same equilibrium mixture, instead of cooling it, we actually allow it to warm up to room temperature, we drive the forward reaction. Okay, we end up with a brown gas. So this just gives you an idea about how reactions can occur in the forward and reverse direction, and it actually gives you something you can actually visualize. You could actually see in the lab if you wanted to do this. So if we take a look at what actually is happening with our concentrations during this process, let's start out by looking at the forward reaction. Okay, so here we're applying heat to the reaction, or applying heat to the mixture, or you could just think of it as we're allowing the reaction mixture to reach equilibrium. But let's think of it in terms of we had the system all the way cold, and now we're allowing it to warm. So what happens? So first let's look at our plots. We have concentration on our y-axis, and we have time on our x-axis. Okay, so let's look at what happens when the reaction proceeds. So we start out with no NO2. So this is, remember, is if we started from the very cold reaction mixture, which was this one, that was colorless. Okay, so we start out with no NO2. We start out with only N2O4 present. Okay, so we start out with some moderate amount of it. As the reaction proceeds, the amount of N2O4 decreases. Okay, so you can see that it's going down, and the amount of NO2 increases. Okay, so that's picturing the reaction from the forward direction. Now, what about the reverse direction? Okay, so now we're starting from the warmed mixture, and maybe we're cooling it down. So let's see what happens there. So as time goes on, we decrease the amount of NO2. So if we're all the way pushed to the right, we start with only NO2, and over time it goes down. And we're starting with no N2O4, and over time it increases. Okay? And when we're in our equilibrium, we lie in this region. So we have some N2O4, and we have some NO2. Okay? And that region would represent our chemical equilibrium. Okay, and they give us some details about the exact concentrations that would be in that equilibrium mixture. So if we take a look at our reaction rate while this is occurring, so now we have reaction rate on our y-axis and time on our x. Okay, what we see is that through time, so if we're again looking at the forward reaction, as N2O4 is consumed, the rate of the forward reaction decreases. So again, we're talking about the forward reaction, meaning we're forming NO2 from N2O4. So as time goes on, the rate of this forward reaction actually slows down. At the same time, NO2 is formed, and the rate of the reverse reaction starts to increase, because remember, it's starting from zero essentially, so it has to increase if we have an equilibrium reaction. Okay, so over time, the rate of our reverse reaction increases. Eventually, once we get to this equilibrium state, our rates become equal. So we're no longer consuming N2O4 faster than we're producing NO2, and we're no longer consuming NO2 faster than we're producing N2O4. Okay, so our rates become equal at equilibrium. So notice we didn't say that our concentrations were equal, because if we come back and look, we still have more N2O4 than we do NO2. Okay, but our reaction rates have become equal. So we're not consuming one faster than the other, and we're not producing one faster than the other. So let's take a look at this general equilibrium reaction. So here we have A2 plus B2, which is an equilibrium with 2AB. And you'll notice we have rate constants of K1 and K minus 1, okay, which is a common way of showing the forward reaction and the reverse reaction. So let's see if we can come up with some rate laws for this. So in general, if we just want to look at the forward reaction, again, A2 plus B2 gives us 2AB. We can say that rate is proportional to the concentration of A2 raised to the x times the concentration of B2 raised to the y. Or we can also say that rate is equal to K1, the forward rate constant, times the concentration of A2 raised to the x times the concentration of B2 raised to the y. And for the reverse reaction, so now if we look at this, we have 2AB giving us A2 plus B2. So just looking at the reverse reaction, okay, so now in the reverse reaction, these what was products now becomes reactants, and what were our reactants now become our products. So now we have the reverse. 2AB gives us A2 plus B2. Okay, so we can say that rate is proportional to the concentration of AB raised to the z. Because remember, when we write these rate expressions, we're only interested in the reactants. We're not interested in the products. And we can say that rate is equal to K minus 1 times the concentration of AB raised to the z. Okay, now let's look at our N2O4 system. So we have N2O4 giving us NO2. That's our forward reaction. Okay, so we can write the rate law. Rate is equal to Kf, in other words, K forward, times the concentration of N2O4. And for the reverse reaction, remember now our products become our reactants. We have 2NO2 giving us N2O4. And we can write the rate expression. Rate is equal to Kr, in other words, the reverse rate constant, times NO2 squared. Okay, so there we have just two general rate laws for this equilibrium. But remember, the forward rate and the reverse rate are equal at equilibrium. So we can say Kf times the concentration of N2O4 is equal to Kr times the concentration of NO2 squared. If we rearrange, so if we just gather all of our rate constants to one side, and we gather our concentrations to the other, we come up with Kf over Kr is equal to concentration of NO2 squared over concentrations of N2O4. So these are our products of our forward reaction, and these were our reactants. Okay, so remember this idea of products over reactants. That's going to come back into play a lot in this chapter, products over reactants. Okay, but if we set this up, Kf over Kr is equal to concentration of our products over the concentration of our reactants. We can set this equal to Keq. Okay, so we're tying both of our rate constants into a single constant called our equilibrium constant, Keq. Okay, so what exactly is the equilibrium constant? What does it tell us? So the equilibrium constant is the ratio at equilibrium of the product of the concentrations of the product of the reaction raised to the stoichiometric coefficients to the product of concentrations of the reactants raised to the stoichiometric coefficients. Okay, so that's a mouthful. But what it actually is if we take a look at our products and we take a look at our reactants. Okay, so the way we want to write our our equilibrium constant is to first take the products. Okay, so you're going to take the concentration. So here we have C of C and D of D. So we have A of A giving us plus B of B giving us C of C and D of D. And we're always going to look at this in the way that the reaction is written, unless, for instance, we're writing the opposite of the equilibrium constant. So if we're writing like the -1 of it kind of thing. Okay, so just in general, we'll take the products. So the concentration of C raised to its stoichiometric coefficient, so C, times concentration of D raised to D. So that handles our product side. Now that's going to be over concentration of A raised to A times the concentration of B raised to B. Okay, so that handles our reactants. And notice again, we have products over reactants. It's going to be a common theme. Okay, so Kc is equal to the product of the concentration of our products raised to their power over the product of our reactants raised to their stoichiometric coefficients as a power. Okay, so our equilibrium constant Kc is equal to our equilibrium constant expression. Okay, so everything on the right is the expression. The value of that is our actual equilibrium constant. So let's try to write this for a reaction. So here we have N2 plus H2 giving us NH3, ammonia. So suppose we were asked to calculate the equilibrium constant for this, or just to write the equilibrium expression. Okay, so here we're going to take our products first. So remember, always products over reactants. So here our only product is NH3, ammonia. We're going to take that concentration and raise it to its stoichiometric coefficient, which is 2 in this case. Okay, and that will be over. Now we look at our reactants. So N2, the concentration of N2, and its coefficient is just 1, times the concentration of H2 raised to its stoichiometric coefficient, which is 3. Okay, so here we have this 3 becoming this 3. And this 2 is this 2. Okay, so I know in the previous section, I warned you not to just blindly copy our stoichiometric coefficients as m and n, but in this particular case, when we're talking about equilibrium constants, we can do that. So that's how we find our equilibrium expression. And if we had numbers to put into this, we could actually find our equilibrium constant. Okay, so here's just a series of reactions, and we're asked to write the equilibrium expression. Okay, so we'll go through these together. I'll give you a few seconds to try to think about them, and maybe pause me in the middle and write them down for yourself and see what you think. Okay, so let's take a look at the first one. So we have PCl5 giving us PCl3 and chlorine gas. Okay, so try to write an equilibrium expression for this. Remember, products over reactants. Okay, so if we want to write equilibrium expression for this, we'll say the concentration of PCl3 times the concentration of chlorine gas over our reactants, which is just PCl5. And that would be our equilibrium expression. Okay, here's another. So here we have N2 plus H2 to give us NH3, ammonia. So very similar to what we just looked at. Okay, so first start with your products. So NH3, and that will be squared because remember, we're going to copy down our stoichiometric coefficient. That's our products, and then our reactants are N2 and H2. Okay, the only one that has a stoichiometric coefficient is H2, which is this 3, comes from here. Okay, the next one, a little more complex system now. So we're going to do the same thing. So we'll just take our products, the concentration of our products, and here we have a 4. So this 4 becomes the power here. And at the bottom, we only have this charged copper complex. Okay, so just copy down the write the concentration of our reactants. Okay, and that becomes your equilibrium expression. Okay, so hopefully you'll get out of those. These should be super duper easy. Now that you know how to write them, these should be no problem. So let's take a look at how we could go about calculating Kc. So now we know how to write Kc expressions, but how will we actually calculate Kc? So here we have a problem that says, suppose the equilibrium at 700 Kelvin, the concentrations of N2, H2, and H3 gases were measured to be 0.500 molar, 3 molar, 1.98 molar, and 1.98 molar, respectively. Wants to know what is the value of Kc. Okay, so how can we do this? Well, first, we need to come up with our Kc expression. So remember, products over reactants every single time. Okay, and we just use our stoichiometric coefficients as the power. Okay, so those should be a breeze. Now what do we do? Well, if we actually want to know the value of Kc, well, look what we're looking at. So we're looking at concentrations. Well, they just told us the concentration of each of these. Okay, so the concentration of my ammonia, okay, was 1.98, and it's squared because of my equilibrium expression. And then over 0.5 molar for an N2, and then H2 was 3 molar, and that's cubed because, again, of my equilibrium expression. So now all I have to do is just punch that into my calculator. Okay. So I end up with 3.92 over 13.5, and our Kc becomes 0.290. Okay, so once you know how to set up your equilibrium expression, it's as easy as just punching in the numbers from the problem, if they give them to you like this. There will be sometimes we have to calculate them. Okay, but in this problem, they gave them to us. So we can calculate Kc very easily from our equilibrium expression. So here's one for you to try. It says calculate the value of Kc for the Haber-Bosch process at 500 Kelvin. Given that the equilibrium concentrations of N2 are equal to 3.0 times 10 to the minus 2 molar, H2 is 3.7 times 10 to the minus 2 molar, and NH3 is 1.6 times 10 to the minus 2 molar. And they give you the chemical equation for the Haber-Bosch process. So give this one a try, see what you come up with for your Kc value. Okay, so remember, first we need to write our equilibrium expression. Okay, so we can say that we know we have to put our products over our reactants, so Kc is equal to products over reactants. In this case, Kc will be equal to, so our reactants this time are nitrogen and hydrogen. Okay, and you bring down the 3 as from the coefficient of hydrogen. And then our products are just ammonia, and it's squared from the stoichiometric coefficient of ammonia in our reaction equation. Okay, so that's our Kc expression. Now just plug in your values. Okay, so just make sure you match up the correct concentrations with the correct species, and you should be good to go. So do this multiplication, you end up with something like this. Okay, so I just kind of wrote it out stepwise for you, and you end up with a Kc value of 168.5. Okay, so hopefully you came up with something similar, and hopefully I didn't make any mistakes. Okay, again, so once you know how to set up the equilibrium expression, just plug in the numbers is the easy part. What if we're dealing with pressure instead? So instead of having a concentration of molarity, what if instead we have pressure? Well, because pressure is proportional to the concentration of a gas in a closed system, the equilibrium expression can also be written in terms of pressure. So I like to think of, and I always say this, that pressure is essentially concentration for a gas. I think that's a good way of looking at it. So if you're dealing with gases, you may write it in Kp, or you may write it in form of pressure. If you're dealing with concentration, you'll probably write it in forms of concentration. Okay, so we have an equilibrium system, A of A plus B of B, gives us C of C and D of D. And here they're telling us that they want us to write our equilibrium constant in form of pressure. Okay, so when it's in the form of pressure, we write Kp. So just like Kc was for concentration, Kp is for pressure. Okay, but it's done exactly the same way. So the pressure of the products over the pressure of the reactants. So here we get P of compound C raised to its stoichiometric coefficient C times the pressure of compound D raised to its stoichiometric coefficient over the pressure of compound A raised to its stoichiometric coefficient times the pressure of compound B raised to its coefficient. Okay, so it's exactly the same. The only difference is now we're dealing with pressure instead of concentration. Okay, so suppose we have this system. So we have methane gas reacting with H2S to give us CS2 and hydrogen. Okay, so suppose we want to write our Kp expression, so our equilibrium expression. Okay, again, we'll take our reactants over our products. I'm sorry, our products over our reactants. Sometimes I say those backwards. Products over reactants. Okay, and we'll write it the exact same way. And notice this power is still our stoichiometric coefficient. Okay, so the 4 in front of hydrogen comes down as its power. And the same thing for our reactants. Okay, so just the same setup as before. Okay, so here's one for you to try. It says methane reacts with H2S to yield H2 and CS2 gases. CS2 is a substance used in manufacturing rayon and cellophane. And it gives us the equilibrium reaction. It wants to know what is the value of Kp at 1000 Kelvin if the partial pressures in an equilibrium mixture are 0.2 atm for methane, 0.25 atm for H2S, 0.52 atm for CS2, and 0.1 atm for H2. Okay, give this one a try and see what you come up with. Okay, so let's take a look at this one. So first write out your Kp expression. So Kp is equal to the pressure of the products over the pressure of the reactants. Okay, so we can say Kp is equal to, we'll start with our reactants. So the pressure of methane times the pressure of H2S squared. And again, the 2 comes from its coefficient here, so this 2 is this 2. My computer a second to catch up, hopefully. Okay, then we have our products. So the pressure of CS2 times the pressure of hydrogen raised to the 4th. Okay, then all we have to do is just plug in our numbers. So they gave us pressure for each of these. So take your Kp expression and just plug in your numbers. And hopefully you came up with something close to 4.0 times 10 to the minus 3. Okay, so again, once you know how to set up your equilibrium expression, it should be pretty simple. So suppose we wanted to relate Kc to Kp. We can use the equation Kp is equal to Kc times RT raised to the delta N. Okay, so this should look familiar. This should look very similar to your ideal gas law. Oops, sorry, I accidentally hit back. Okay. So this comes from the ideal gas law, where we know PV is equal to N times R times T, where P is our pressure, V is our volume, N is the number of moles, R is the gas constant, and T is the temperature. So if we rearrange, we get P is equal to N over V times R times T. Okay, so how do we get from there to get to this Kp is equal to Kc times R times T? Okay, so remember that Kc is equal to the concentration of B of our products over the concentration of our reactants, here A, and Kp is equal to the pressure of B over the pressure of A, products over reactants. So now we can plug this in, say that P is equal to N over V times R times T. But remember, Pb is equal to N of B over V. So the pressure is the number of moles over the volume times R times T. So N over V, moles over volume, what does that sound like? Moles over liter. That's our concentration of B. We can also say, and in other words, we can rearrange this to say that Pb is equal to the concentration of B times R times T. And we can write that P of A is equal to N of A over V times R times T. And again, N of A over V is the concentration of A. And we can rewrite this as the concentration of A times R times T. Okay, and then remember that our Kp is equal to Pb over P of A. So we can rewrite this as concentration of B times R times T raised to the B, okay, whatever our coefficient is equal over concentration of A times R times T raised to the A. Okay, which just becomes concentration of B to the B times RT raised to the B times the concentration of A raised to the A times R times T raised to the A. So in other words, what does this seem like? Seems a lot like Kc times RT over RT. Remember, this term, so I'm not able to write on my screen at this particular moment, but remember that B, concentration of B over the concentration of A is equal to Kc. Okay, so Kc, or Kp is equal to Kc times R times T raised to the B minus A. Okay, and this B minus A is equal to the delta N, where delta N is the number of moles of gas products minus the number of moles of gas reactants. Okay, so my final expression again, Kp is equal to Kc times R times T raised to the delta N. Okay, and note that Keq can represent either Kc or Kp, so we can use those terms interchangeably. But understand this is how we relate the two. Okay, I'm not going to expect you to know how to get this whole derivation, but just understand that there are roots that this comes from. Okay, so suppose we wanted to know what is the value of Kp given that Kc is equal to 5.4 times 10 to the 13th at 25 degrees C. How can we find this? Okay, so remember Kp is equal to Kc times R times T raised to the delta N. Okay, so we want to know what Kp is. We're given a Kc. We know what R is, 0.0821 liter atmospheres over mole Kelvin. And our temperature is 25 C, convert that to Kelvin, 298 K. Now our delta N, we have to take a look at our stoichiometric coefficients. Okay, so in other words, take a look at our total moles of gas. It's going to be the total moles of gas of the products minus the total moles of gas of the reactants. Okay, so here we have 2 moles of NO2 on our product side, so that's just a 2. Our reactant side, we have 2 moles of NO plus 1 mole of O2, which is a total of 3. Okay, so our delta N is 2 minus 3, which gives us minus 1. Okay, so just plugging everything back into Kp, we end up with 5.4 times 10 to the 13th times R, times our T in Kelvin, raised to the minus 1. And again, the minus 1 comes from our delta N. So just the difference in the moles of gas of the products and the reactants. Okay, so we come up with this as an answer. 2.2 times 10 to the 12th. That's our that would be our Kp value, since this equation gives us Kp. So they gave us Kc, we were asked to find Kp. Okay, so here's 2 problems for you to try. It says hydrogen is produced industrially by the steam-hydrocarbon reforming process, and that gives us water, plus methane gives us CO and H2. The first one, it says if Kc is equal to 3.8 times 10 to the minus 3 at 1000 Kelvin, what is the value of Kp at the same temperature? The second one asks you if Kp is equal to 6.1 times 10 to the minus 4 at 1124 degrees C. What is Kc at that temperature? So the first one wants to know what's the value of Kp. Second one wants to know the value of Kc. So give this one a try and see what you come up with. Okay, so for the first one, we just need to grab our Kp expression. So they gave us a Kc, they gave us our temperature in Kelvin. We know R, so we need to calculate the delta N. So our delta N, if we look at our products, we have 3 moles of H2 plus 1 mole of CO, so that's 4. Then our reactant side, we just have 2 moles of gas. So we have 1 mole of H2O and 1 mole of methane, so that would be 2. Okay, so our expression becomes our Kc value, so 3.8 times 10 to the minus 3, times R times 1000, raised to 4 minus 2, because our delta N on our product side, we have 4 moles of gas. On our reactant side, we have 2, so our delta N becomes 4 minus 2. This gives you a Kp value of 25.6. Okay, the next one, we have a Kp value, but we want to find Kc. So we'll take the same equation, but now we'll rearrange to find Kc. So just rearrange to say that Kc is equal to Kp over RT raised to the delta N. So in other words, just divide both sides by RT delta N. Okay, and then convert your temperature to Kelvin. We know the value of R, we know the value of Kp, so now you just need to plug those in. Okay, you end up with a Kc equal to 4.6. Okay, so hopefully nothing too difficult there. One just rearranging the equation, plugging numbers in. The first one, really just plugging numbers in. The only thing that might have been complicated is calculating delta N, but hopefully now you realize how to do it. Okay, so it's just the moles of gas of the product side minus the moles of gas on the reactant side. Okay, so I think that's a good place to break.